Hello, Augies Worldwide. I'm Dave Kassler, amateur radio call sign KE0OG, here with another episode of Ask Dave. Today I'm going to answer a viewer question trying to understand the difference between frequency and wavelength, two very closely related concepts that turn out to be kind of the inverse of each other. But let's go through a few charts, because if we want to go all the way back to the beginning, let's go all the way back to the beginning. Let's take a look. In order to determine how long electromagnetic waves are and how you determine the frequency, we need to understand how fast do electromagnetic waves travel. It took quite a while for scientists to understand, first of all, that electricity and magnetism were two sides of the same coin. You can't have one without the other. We're talking about the 1700s, and some of the scientists in England and Germany and France were the key areas where this research was taking place. I mean, this is the period of time where the guy named Ohm was trying to understand the relationship between voltage and current and resistance. And he came up with Ohm's law, but Ohm's law was anything but widely accepted at first. I mean, these were the times when things were just being understood here. Now, lots of early scientists thought there had to be a medium to carry these electromagnetic waves. Think of it, sound waves, you have to have air. Contrary to the shirt I have on, in Star Wars where you hear all these booms in space, there is no sound in space because there's no air to carry it. Okay, you think of the waves on the sea, that's the water, all that sort of stuff. So they invented something to be a medium for the electromagnetic waves. And this misconception lasted for many, many, many years. And what they called the medium that carried electromagnetic waves was the, are you ready for this, luminiferous ether. Luminiferous ether. Now, they started to run into problems with this ether thing when every new discovery needed something to propagate it, and so they created a new kind of ether. And the ether for carrying a light was the luminiferous ether. Lumen is from the, I think it's the Greek or Latin, one of the two, for light. Okay. Now, the next big conceptual leap that came along was the discovery that light and the waves that propagated, like from spark radios and things like that, Heinrich Hertz's experiments and so on, that light and electromagnetic waves are fundamentally the same thing. They are electromagnetic waves traveling through an electromagnetic field. Now, a field is... You can think of it as, a farmer's field, but actually it is a mathematical concept that I had to study when I got my math degree, that has certain properties, additive, and so on. You can superimpose waves on one another. That it has these mathematical properties. Well, as it turns out, it's the electromagnetic field, which again is a mathematical conception, not a real thing. It's a mathematical conception. You might as well treat it as real because it behaves like it's real. But light and electromagnetic waves are the same thing. Now, two key points were proven early on. None of these were obvious. Okay? All electromagnetic waves travel at the same rate or same speed, regardless of the frequency. So green light and red light traveled at the same speed, and a 100 megahertz wave travels at the same speed as a 1 megahertz wave. That was not obvious early on. People thought that waves of different frequencies might travel differently, but they don't. They all traveled at the same speed. The next thing that came along was that no medium was needed for this. The Maxwell came up with 21 equations, which Heaviside reduced to 4, that explain how all this works without having to have a medium. So this was hard for a lot of people to accept, and it is still hard for new hams to accept the idea that these waves can travel around the world and they don't need any kind of a medium to do it. They're, when we talk about waves wiggling through the air, they don't wiggle through the air. It's a potential charge that moves along. But there's got to be an ether. So you will occasionally hear the term ether. Are you going to put anything on the ether tonight? Something like that. You'll occasionally hear that. It's just a kind of a reference to, there's got to be something that does this. Now, the third thing that, 2 key points. Okay, let's change that to 3 key points, okay? The last thing was that the speed of light is not infinite. Now, the early Greeks got in on the action here, though they went way off in the wrong direction. They felt that light didn't travel at all. Light beams came out of your eyes and touched upon the things that you could see. Okay, I guess if you're a Greek in 200 BC, that makes sense. Okay, and it took a long time to figure that out. There were a lot of people who thought the speed of light was infinite. These are people who thought that, like the Newtonian universe, where there was no curvature of space-time and so on. But they did find out, there were experiments done early on to find out that the speed of light is finite. It has a speed. It's very fast, but it's finite. It takes 8 seconds for light to get from the sun to the earth. Okay, we've got a space probe out past Pluto, and it takes hours for a signal to get from Earth to that spacecraft out there. Now, Albert Einstein came along in the beginning of the 20th century and showed that the speed of light, which is universally called c, is a fundamental universal constant. And that doesn't matter what your frame of reference is, the speed of light is always the same. And it turns out lots of things depend on the speed of light. Some fundamental universal constants, when divided by each other, yield the speed of light. Albert Einstein went a little further and made some early breakthroughs in defining light, and hence all electromagnetic waves, as photons. Photons are particles. And so you ask, well, is light or electromagnetic waves or a particle? And the answer is yes, it's both. Now, we don't normally think in terms of photons when we're talking about our dipole antenna in the backyard. We think in terms of waves. It's just much easier to do. Are there photons involved? Yes. Is that a good way to explain what's going on? No. It's just, we'll use waves for ham radio. And photons work well for light, but you got to take a look at the wave phenomena at the same time. Well, let's go take a look at a mechanism that was used in the 1930s to try to determine the speed of light. This is a mile-long tube, and it's been evacuated. It's got a vacuum in it. And there was a Dr. Michelson who worked with some others there to bounce light back and forth between mirrors on the end. And this is the kind of the thing that shows how they could do it. And it shows how you could measure the speed of light. And they came very close. It turned out to be important in World War II when radar was invented. I'm talking about the kind of radar that is where you ping something and you wait for the ping to come back. The radars used by the British were continuous wave radars and were a lot different from the pulsed radars. The pulsed radars, you actually have a cathode ray tube that is calculating where that pulse is right now, and it pings off an airplane and comes back to you. That time actually is just converted into a distance on the scale, and that's how radar works. So how fast does light travel? Well, c, the speed of light, is the same in all inertial reference systems. That's Einstein's big theory of, I think it's special relativity, that it doesn't matter how fast you're moving. If you're moving half the speed of light away from somebody else, to you, the speed of light stays the same. It's relativity. Now, we now define the meter, how long a meter is, in terms of the speed of light, because the speed of light is a constant. It's a universal natural constant. And in a vacuum, it's 299,792,458 meters per second by definition. Okay? Or the other way of looking at it, 1 meter is how far light travels in 1 over 299,792,548 seconds. Now, I don't think that's a terribly useful definition. I'm not going to be able to construct the meter from that, but I don't know, the people who do these things for the international conventions on metrics and so on say that they want to define all the metrics in terms of some natural constant. It used to be that the meter was the length between 2 scratches on a platinum bar in France. And that was by definition a meter. It was supposed to be 1/10,000th of the distance between the equator and the North Pole on a line going through Paris. Now, one of the problems with that is that the Earth wobbles on its orbit. So where is the North Pole? Well, it wobbles around, so that changes the definition of the meter. So they made this meter bar that you could use, and now they've redefined it fairly recently in terms of the speed of light. Now, usually we say, instead of light travels 299,792,458 meters per second, we say light travels 300, since that's very close to 300 times a million. 10 to the 6 is a 1 followed by 6 zeros. 10 to the 6 meters per second. Or more usefully, light travels 300 meters in 1 microsecond. Microsecond is easily measurable by modern equipment. Now, a couple things to note about the speed of light. Light slows down when it's not in a vacuum. This has to do with the index of refraction and stuff like that. We won't go into that. This isn't a physics course. We're talking about radio waves here. In air, light travels at 0.9997 of the speed of light. And usually that tiny, tiny, tiny difference is ignored in practical work. Now, there is something to note that radio waves don't just travel in air or in a vacuum, but electricity can travel in copper wire. In copper wire, the velocity factor is the difference between the speed of light and the speed that it actually goes. And it's about 0.95 for wire. Now, if you're going to go into coax, some coax has a velocity factor of 0.67, others has velocity factor of about 0.88, and so on. You have to look up for the particular coax what it is. But in copper wire, which is what we make dipoles out of, it's about 0.95. And we're going to have to consider that, because if you cut a dipole for the true half wavelength, it's too long. And we'll go into that. Now, I want to introduce the concepts of frequency and wavelength when we're talking about light and electromagnetic waves. And I'm going to just step back a couple hundred years here and say, pretend for a moment that an electromagnetic wave is a vibration in the luminiferous ether, because it's just easier to conceive of that way than voltage variations and magnetic variations in an electromagnetic field, which is what it actually is. Okay, frequency is the number of times per second that a wave goes from the most positive to the most negative and then back to the most positive. In other words, one complete cycle of the wave. Now, actually, when we measure this, we generally measure from the positive going zero crossing to the next positive going zero crossing, which is the same thing. Where you start to measure the wave is arbitrary, as long as you end up your measurement in the same place one cycle later. Frequency is measured in hertz. After Heinrich Hertz, the one who proved that there are electromagnetic waves. Now, as a convenience factor, I'm just going to toss this out here. If instead of 1 second we use how far light travels in 1 microsecond, then any calculations we do using microseconds instead of seconds, the frequency will be in megahertz. 1 microsecond is a millionth of a second, and a megahertz is 1 million hertz, or vibrations, or cycles. Used to be called cycles per second. The change to hertz actually happened during my lifetime. And it took a long time to get people to say hertz instead of cycles per second. And there are still hams out there, you know who I'm talking to, who call it CPS or just cycles per second, or cycles instead of hertz. If you see CPS, it means the same as hertz. Now, that's frequency. How often something happens. Wavelength is the distance that a single cycle of a wave travels, and it's measured in meters. Okay, why not feet? Well, because it's always been meters. Initially, people didn't use frequency, they used wavelength. And so the 80 meter band, which is from 3.5 to 4.0 megahertz, is actually 80 meters is the length of 3.5. And then if you go up to 4, it's actually 75 meters long. 80 meters is a weird band in terms it's so wide compared to the base frequency. So if you think about it, on the 80 meter band, it's a half a megahertz wide out of 4 megahertz. That's like a factor of 1 to 8. But you go into the 7 megahertz band, which is 350 kilohertz wide, and you divide that by 7, you get a much, much smaller number. And that is why a dipole can cover all of 40 meters, but not all of 80 meters, because 80 meters percentage-wise is so wide a band that you can't cover it with a single diode or a single dipole. Okay, let's go to this. Now, I apologize. What you're looking at are the red sine waves in there. And I apologize, these are some I made when I was doing the technician videos, and I only made them 1 pixel thick. So a little bit hard, but they're right here. It's the red that's right in here. This is 1 microsecond in time. This is time here, okay? And this upper wave completes 4 cycles in 1 microsecond. So therefore, it is a 4 megahertz wave, 4 megahertz wave, okay? Now look at this one down here. It completes 8 cycles in 1 microsecond. So it's an 8 megahertz wave, The upper one's 4 megahertz, this one's 8 megahertz. Now notice right away, the wavelength goes from the positive going zero crossing to the positive going zero crossing and is this long right here, okay? Now we go to the higher frequency wave, which, since it's traveling at the same rate as the other wave, because all frequencies propagate at the same speed, you'll note here that because it vibrates faster, the actual length of one wave is half. So when the frequency goes up by a factor of 2, the wavelength gets divided by a factor of 2. This is the fundamental thing about frequency and waves that mixes people up. Nowadays, all radios, we set the frequency in, okay? And we can get it very accurate to within 1 hertz out of 10 million. Okay, it's 1 part per 10 million. That's pretty good. But the wavelengths, the names of the bands have stuck. Like I said, 75 meters is 4 megahertz, and that is considered to be part of the 80 meter band, but it's obviously not 80 meters. If you go to the 10 meter band, 10 meters is actually 30 megahertz, but no part of the 10 meter band contains 30 megahertz. It's just a naming convention that's stuck for a long time. Let's get into just a little bit of practical stuff if we can. Wavelength is the inverse of frequency. The frequency in megahertz is equal to 300. Now this is the speed of light for a microsecond. And that's why we've got megahertz over here. Megahertz is 1,000,000. Microsecond is 1 millionth. So it's 300,000. It's 299.99, it's 300. We'll use 300. Now you can always swap what's in the denominator here with what's in the numerator over here. So wavelength is 300 divided by the frequency in megahertz. This bottom one is the one that we're going to use to calculate the length of an antenna. Now the fundamental antenna in amateur radio, and actually in almost all work with electromagnetic waves, is the dipole. And you'll find dipoles in the strangest places. When they end a piece of waveguide and they want to illuminate the parabolic dish, they will have a little dipole right there, and that waveguide feeds that little dipole. Little dipole might only be 1 inch long. If somebody says dipole without otherwise qualifying it, it usually means half wavelength. Usage in ham radio is loose and has been loose for many years. Some people think dipole means an antenna that's just cut in half and fed in the middle. But the dipole, unless you say it's 3 halves or off-center, well, off-center fed doesn't matter. A dipole is a dipole is a dipole. It doesn't matter how you feed it. You can feed it in the middle, you can feed it off-center, you can feed it at the end, whatever it is. But it is the fundamental electric field resonant antenna. Now, are there antennas that are not electric field resonant? Yes. There are so-called wave antennas like the rhombic, which is not a resonant antenna. You've got your G5RV, which is not a resonant antenna. You've got the all different kinds of antennas, but your fundamental antenna, fundamental electric field resonant antenna, is a dipole. How you feed it doesn't matter. To make a dipole, a half-wave dipole, we can compute how long it needs to be 1/2 wavelength, because dipoles are a half wavelength long. Note that lambda, that's that funny Greek letter right there, is often used to represent wavelength. Wavelength, which is, a long word to spell out, we just use lambda. Now don't forget that the velocity factor in wire is 0.95, so we're going to have to shorten the wire so that the wave can get all the way through it in the right amount of time. So here, let's just walk through this kind of across. The wavelength in meters is 300 divided by the frequency in megahertz. There are 3.281 feet per meter, so the wavelength in feet is 300 times 3.281 divided by the frequency in megahertz, or 984.3 divided by the frequency in megahertz. But we want a half wave, not a full wave. So a half wave is half 984.3, which is 492.15, something like that, okay? This is the electrical length of a half wave in a vacuum, so we need to do it in copper. So we have to multiply it by the velocity factor of 0.95 right there. So the half wave in feet is 492 times 0.95 divided by the frequency in megahertz, and lo and behold, look what we come up with. The grand old formula that's been around for 1,000,000 years that says that a half wave dipole, the whole length of it, not half of the dipole, but the whole dipole is a half wave, is 468 over the frequency in megahertz. And there, I just showed you how all that worked. Okay, so this was just kind of a little look at frequency versus wavelength, how they relate, how it goes back to a few fundamental principles that were discovered by the big leading lights in electronics back in the 1700s and 1800s, and some of it, like actually calculating the speed of light to great precision, was done in the 20th century. So lots of interesting stuff. And what do we come out with this? We learned that wavelength's the inverse of frequency, and you can use these numbers that I've got on the chart here to calculate that. So I hope that was helpful. If not helpful, illuminating. We got to use some term that means light, so illuminating. And I hope this helps you kind of appreciate a little bit all the things that have been played with. None of this was obvious to anybody 300 years ago. Nobody knew any of this. This is new knowledge. This is not knowledge that came down to us through, I don't know, monks illustrating their manuscripts. This was all discovered since then. It's very interesting, fascinating. I think you can tell I really enjoy this. I hope that you really enjoy this. If you do, please subscribe and please click like. If you subscribe, that tells YouTube that this is a channel that you think other people should see too. If you click the bell, you'll get a notification. However, YouTube notifies people. They stopped doing email notifications a while back, and I'm an email kind of guy, so I don't get notifications for my channels. But there you are. If you would like to support this channel financially, please take a look at dcasler.com/support. That's dcasler.com/support. There are lots of different ways that you can do that. Pick one that you like, or if you just like to continue enjoying these videos for free, they are absolutely free on YouTube here. So, until we next meet, 73.